to talk about the status of and future prospects for thinking about homology, and I'll put cohomology in HOTT. So, based on a couple of theorems we've recently proved, we're getting very close to being able to really talk about these things inside HOTT. So, but today, I think what's going to happen today is I'll probably give more like an overview of how we can think about these things sort of in a homotopy invariant way, what they are, why they're interesting, and things like this. And then I will try to say as I go what kinds of things we are sort of accessible for us at this point. So that means that I'm going to talk probably more like an algebraic topologist in this talk than a type theorist for describing, because I'm going to try to describe what these things are to an algebraic topologist, and I'll try to sort of bridge the gap in between to describe what we can do and where we might go. Okay, where should we start? So let me start with a certain idea that's familiar to algebraic topologists, and then develop it a little bit. So if you give me a map, and maybe just to get used to my notation and how I write these things, I think we saw there's two things I can do with it. So I'll put one over here. Actually, maybe I should put one down here. F to y, right? On the one hand, you can map x to a point right here, and you can take the homotopy push out of this, which is something we do in Coq. Something we can define. It would be a higher inductive type. Actually, maybe I should start with this version over here, because this one is more easy. I can map a point. Oh, by the way, everything in this talk is going to be based. So I'm going to always work with based types, and meaning meaning a type, pointed together with a chosen point. Okay, so we're sort of working in the category of pointed types. And that's just going to be a convenience. Certain things are annoying. I think in Coq it's not so bad maybe to work with pointed types, and Agda it's a bit of a pain. But in any case, it's more of an inconvenience. It's a little more inconvenient in type theory, but for what I'm going to do today, it's extremely convenient to just always work with pointed types. Okay. There's a couple things I can do. So you give me a map F, and y is pointed, so I can map a point in at the base point. And I can take the homotopy limit of this diagram, as Jeremy was talking about the other day. And what I get is called the fiber of F, the homotopy fiber of F. I'm going to write it as a capital F of F. But I can continue like this because x was pointed, so I can map x in right here. And if I take this pullback now, and let me call this map P, then it by definition is the fiber of P. So that's the fiber of P right there. But on the other hand, if I look at, and it gets a map like this, but now both of these squares were pullbacks, and if I look at the outside one, did I do this wrong? Nope, that's OK. It tells me that this is loops on y. OK?
Could that be any smaller?
I can do it smaller. Is that OK? It is loops on y. Is that OK? OK. Let's see. But now this thing obtains a natural canonical base point, right? So I can map a point in there. And what is this map right here? So let's call this map Q. And then I can take the fiber, and I will get the fiber of Q. Right? But now I stare at this diagram, and I say it was both of these are pullbacks, which means that that the outer square is a pullback too. So this must be equivalent to loops on X. Okay? So this is this cute trick, and if you follow this path like this, you can go forever, and you will just keep getting loops and loops and loops. And this is what people call the fiber sequence for the map F. So and it looks like this: the fiber of F And then we get loops on y, and then we get loops on x, and then we get loops on the fiber of f, and then we get double loops on y. And this just keeps going forever. So given any map, I can just generate a sequence like this, right? I want to illustrate how people use these sequences in algebraic topology. So, but dually, I can do the exact same thing over here, where I just work on the dual side. So now I map x to a point, and I take the push out. And I'm going to call that C sub f, and call this I. And this is the mapping cone on f. A homotopy theorist would draw a picture like this. They would draw y, and then they would draw something like this. Because and as a higher inductive type, what you're saying is that you take in left of y, you have a point for every y, and then you have a point for the base point. And for every point in x, you glue a line from the base point to the image of f of x. So what you get is a picture that looks like this, the mapping cone. It's a higher inductive type. It's also the homotopy push out of this square right here. So I don't know if you can sort of see this, but right. I mean, so it's nice to get used to these homotopy push-outs. Like if I draw that push-out diagram right there as something like this, then you can see what I have is you can view the homotopy push-out as kind of like a here's y, here's x, and here's a point. It's sort of like a fibration over this push-out diagram right here, where I consider it as an interval. Y lives over this point. Over the point in the middle, I see x, which is the thing in that circle right there, and over this point, I see a point. And so I sort of glued everything together. Okay, but now I can continue. Let's see. So which way?
You didn't really say it's like a vibration, did you?
I did say it's like a vibration, and it is a vibration, right?
Which map is a vibration?
So if you have a diagram of spaces over a category, and you map this to type, right? Then it's useful to think of the homotopy colimit of this. It will have a map to the nerve of C. And that map is sort of essentially a fibration modulo some details. Okay.
As a higher inductive type, we could force this one to be a vibration.
Yeah.
Which would be equivalent to topologically taking the fiber replacement.
Of the nerve, right? Exactly.
Wait. But the fiber, what is the base of this vibration? In the example of homotopy push-out.
It's just an interval. So.
But the fiber over one point of the interval is
Ah.
y, and the fiber over another is
Okay.
one point, which is not.
You're right. So it's not a fibration in the topological sense. It's a fibration in the higher categorical sense, right?
It's a family.
It's a family, sure. Okay, let's not belabor this point. Okay, I just wanted to draw a picture of how I think of the homotopy colimit.
Fundamentally shouldn't change homotopy type.
Yes,
So over any-
you're right. I think okay. It's a family. Let's just stick with that. Okay. But the point, so I can do the same thing over here. Now, so which way do I want to map a point in? Oh, I want to map y to a point, right? And so this will give me the cofiber of I right here. And then I keep going. So I map CF to a point. So I'm just doing the dual picture over here. And oops. Oh, yeah. Right. But over here, now the exact same lemma applies to say that this is a push out and this is a push out. So the outside is a push out, which means this thing is equivalent to the suspension of x. Okay? Because if I take x and I push it out along 2 points, then that's this picture. Sorry, I'm going to keep drawing it, even though it's not a vibration. That's x here, a point here, and a line glued in for every thing in the middle. Okay? That's what that homotopy push out would be right there. Suspension of x.
And F doesn't play a role in what you obtain?
F does play a role. It played a role in this space right here. It told me how to glue the cone on x into y.
But not in the next term.
Yeah. Right.
Next term somehow F is lost.
Right. Yeah. Just like over there. Right. Because you can imagine the next term is like when I take intuitively it's like smashing y to a point. So if all the information about f was in how I glued x to y, but then if I smash y to a point, that information is gone, and all I see is like x that's left.
Maybe you could draw a picture.
Yeah. Right. So I guess the standard picture would be something like this, and then you glue a cone over here as well. So now this piece is contractible as well. And so when you contract it down, what you're left with is this thing with x in the middle, which is sort of right here. When you contract that side down, you get something like that. Okay? And then right. So then I want to do this again, right? So then I map this to a point, and then I see here this will be, I'll call this J. This is the cofiber on J, except for again the same argument. This is the suspension of Y by looking at the outside square. Okay. So the dual thing is that given a map x from F to Y, I can generate this sequence as well. Okay, so this is called the cofiber sequence. And this is called the fiber sequence. Why do people use these things? Okay, let's see. So now let's suppose space Z. So by space I mean type, pointed type, whatever. We're working in the pointed category. So why do people use these? Because if I map Z into this sequence right here, something interesting happens, right? So if I can look at the following sequence, I can take, I'm going to look at the fiber sequence first. I can take maps into, let's see if I'm going to do this the right way. Let's see if I get it right, into Z, right? And then I can take map from X into Z. And these are pointed maps, so maps which preserve the base point up to propositional equality. Map from the fiber of F into Z. I want the other way. Sorry. I knew I was going to get it wrong. It's one or the other, right? I want to map into this thing, right? Okay, so I want to map. Let's try it again. Map Z into Y, and then map. Yeah, sorry, that was what I wanted. I want to map into the fiber sequence. So map Z into Y, Z into X, map Z into the fiber of F. Okay, I need to be more careful and give myself room. Z into loops on Y, et cetera, et cetera. I get a sequence like this, okay? Now, but now what I want to do is I'm going to give an argument. So what I can do is now I want to truncate these maps. So in other words, I want to just look at the connected components of these maps. Okay, so I look at this sequence, and then I take tau naught is like saying homotopy classes of maps, right? Two maps from Z to Y are homotopic to each other if and only if they're sort of in the same component in this mapping space. So if I look at the set of connected components, I'm looking at the set of homotopy classes of maps, right? So I truncate down to a zero set. And what's the point of this? So each of these has a particular base point. And this sequence is exact in the following sense. So let's just look at, so suppose I have F in this term right here. So it's a map from Z to X. I don't have F. Suppose I have phi. That's an ugly phi. Right here. Okay, so each of these, remember, each of these spaces has a canonical base point, the map that sends Z all to the base point of Y, the map that sends Z all to the base point of X. Now, suppose that under this map, phi goes to the base point. Okay, so I should call this map F lower star. So F lower star of phi is the base point. I'll just write it as star. Sorry. Then I claim there exists a unique map here, psi, such that what did I call that map? P lower star of psi is phi.
Not
What?
unique. Not unique.
Not unique. Not unique, okay? And what this says is, so I can define, since these are pointed, I can define the kernel of this map makes sense. It's all the maps here which are taken to the base point. And so what I'm saying here is that this map here is onto the kernel, right? So the image of this map is exactly the kernel of this map right here, okay? And does that make sense? So that's the definition of exact. So exact is kernel of f lower star is the image of p lower star, where I replace f and p by whatever the appropriate map is right there. Okay, so that's what it means to be exact at this spot. Okay, this is essentially clear from the universal property, right? So there's many different ways to look at it, but since x f y star fiber of f p, right? Sorry.
You said that you showed that the kernel is containing the image, but you didn't show that the image is containing the kernel. I guess it's obvious, but
So yeah, it's going to be obvious from the way I draw the diagram right here. But yeah, that's both. Okay. So I claim exactness is just a restatement of the universal property of this diagram, right? Because what I'm saying is I have a phi right here which maps to x. I can always map z to a point. So the f star here is just takes this phi to post composition with f. So if I post compose with f, and I have and it is null. Sorry, yeah. If f composed with phi is null, that means exactly that it factors through a contractible space. So if it's null, I can complete this diagram like this, and then I get a unique map like this by the universal property of the push-on. Not unique, right? Okay. So and conversely, if right. So I claim it's just exactly the universal property of that push-out diagram, which states that this is exact in this spot right here.
I just corrected you by saying it's not unique, but somehow I would like to understand that better, because from an multiplicative viewpoint, it looks that this is unique, right?
Yeah.
So what's going on? Because
Choose the homotopy,
which makes the bigger diagram commutative, and then only then it's commutative. Okay. And the case of this homotopy corresponds to a leaf. So it's the choice of a proof that f composed with phi is 0, so to speak.
Yeah.
And from that you can lift, but there are many proof of that.
Right.
So is this what you
Yeah,
said? Okay.
that's exactly right. Yeah. Yeah. Right. Okay, does that make sense? So this statement is a exact sequence of pointed sets for any space Z, but as soon as you get into the range of loops right here, you're mapping into something which is an H space. So this thing, as soon as you get to this point right here, maps from Z into loops of Y has a multiplication on it, just by multiplying pointwise the loops. And as soon as you get to here, that multiplication is abelian. So this starts out as a sequence of just pointed sets, and then it's groups, and then from here on it's abelian groups. Okay. And okay. So let's go over here. And of course, the same thing holds for the cofiber sequence, where I take taking tau naught maps from X, or I'll just say view this as a functor like this, makes the sequence Yeah, tau naught. Makes the sequence exact. Okay, so so if I map, so what I'm saying is if I truncate and map out of a space into a fiber sequence, I get an exact sequence. And just if you just chase the universal properties the other way, if you take a co-fiber sequence like this and map it into a given space, you'll have the same property that this is exact. Okay, and this is an extremely useful sort of calculational tool. Because, for example, if you choose the space over here to map into to be S naught, then this will recover for you the long exact sequence in homotopy groups. Okay, this just reads pi naught of y. So homotopy classes of maps from S naught into a space are just connected components of that space. Base maps, of course. Yeah, everything's base today. Then you'll get pi naught of x, and then you'll get pi naught of the fiber, and then you'll get pi, well, so, and again, yeah, another thing that I'm going to use implicitly, you'll get the truncation of maps from S naught into loops on y, and I'm going to sort of use this equivalence that in the base category, maps from a suspension are equivalent to maps loops. So in the base category, suspending something and looping it are adjoint to each other. So at this next step, I have S naught into y, so it's into a loop. So I move it over the other side, and I get the suspension of S naught. So I have S1 into y. Well, that's just pi 1 of y. And then I just keep playing the same game. Pi 1 of x, I get something like this. So a particular case of this says that the homotopy groups in a fibration sequence are exact. This is an exact sequence of groups, okay? And that's an extremely powerful calculational tool. Okay. So, well, sometimes. I mean, this turns out to be sort of not that powerful a calculational tool when it comes to calculating homotopy groups, right? And that's sort of what I want to explain next. But that's exactly what we're going to talk about next, right? So the question is, so now I wanted to say one reason. So why are homotopy groups so hard? Or maybe here's one reason why they're hard, right? Is that, well, they play nicely with fibration sequences. That's great. Except for at least from a topologist point of view, most spaces don't come to us presented as fiber sequences. They come to us presented as co-fiber sequences. So typically, a topologist thinks of all these spaces being CW complexes. And then a CW complex is something like has a bunch of skeleton. And if I map a circle into a skeleton and take along F and take the co-fiber here, take a point, then this thing is what people sometimes write xn union along F of an n sphere. In other words, if I have a CW complex, it's built inductively by taking co-fibers of maps from spheres. This is what we mean by gluing on cells. And very often, many spaces that you're presented with in topology, you know how to describe the space as built from attaching maps of spheres. In other words, you can present its various skeleta as maps in this co-fiber sequence right here, right? So you know how to glue on spheres, how to build the space you're interested in. But if you want to calculate its homotopy groups, that's not great because the homotopy groups work over there, okay? But so what can we say? Let's take, so I claim that, that the Blakers-Massey theorem, this theorem that we sort of now know how to do, says that, well, it's not true that this sequence is exact for homotopy groups, but it's exact in a range, depending on the connectivity of the spaces. So let me sort of derive this statement, or try to, see if I get it right, that this sequence is kind of exact in certain places. OK, so just recall the Blakers-Massey. Sometimes people call it the homotopy excision, and we'll see later why. It says the following. It says that if you have a pushout, a homotopy pushout square, where F is n connected. OK, so now we're going to run into this problem. G is m connected. Then the map A, so this is a push-out square, but I can take the pullback of C and B along D. And so I get C crossover D with B is, and now here it depends what convention we take, but I'm just going to pick the convention that makes this easiest, because it's going to make this easiest for all of us. OK, so based on this theorem, I will tell you what I mean by n connected. So, so this is going to be the HOTT version of n connected, meaning that a map is n connected if and only if all of its fibers are n connected. OK, so this is, Peter talked a little bit about this slight ambiguity, but it's going to be just easiest if we think of this. OK. So I'm going to state it in this form, and this unfortunately disagrees with topological literature, but it'll be easiest for us. So or at least for me, because I won't have to keep track of these indices so badly. And in some sense, it seems like it's kind of the right definition, doesn't it? OK. OK. So let's see what we can learn if we apply this to a cofiber square. So let's take a push out of, let's generate our cofiber sequence and see what we can learn. So let's suppose X is n connected, which with this convention, that's the same thing as saying the map to a point is n connected. And F is m connected. So what do we learn? So, well, here's I. So we learn a couple of things. So the most obvious thing we learn is that the homotopy fiber of this, so the fiber of I, is n plus m connected, right? Meaning the fiber, the homotopy groups of the fiber agree with the homotopy groups of X up to n plus m. Okay, that's one way to say it. N is surjective and n plus 1, but that's not going to matter. In particular, since X is n connected, that means at least the first n homotopy groups of this fiber are 0. But if that's true, This is not what I wanted to say. This did not come out like I wanted to. Well, I did it in the reverse order that I wanted to, so that's OK. That's not so interesting, is it? Let's view this another way. So so I want to give you a different presentation of this map right here. So on the one hand, I can take this pullback right here. So this would be the fiber of I. And the Blakers-Massey says something about the vanishing of the homotopy groups of the fiber of this map. Another way, but this map, its fiber can also be obtained a different way. I can also take the fiber of this map and the fiber of this map. So let me call that f sub f. And the fiber of this map right here is just loops on C sub f. So here I just for any map you can generate the fiber sequence. So I just generated the fiber sequence this way. Okay, but then there's an induced map here, since this is just a natural transformation, and I can look at the fiber of this map right here, and let me call that T. And I claim that T agrees with the fiber of this map right here. Does that make sense? Do you want me to prove that, or do you care?
What is T again?
T is one of two things. On the one hand, it's the fiber of this map to this pullback. So this is a fibration sequence. On the other hand, it's the fiber of this map right here. So this is a fibration sequence.
That's the same thing by construction, so to speak.
Sure.
Okay.
If you agree with this, that's fine. I mean, I know a proof, but maybe I don't want to go so far as to say what it is.
T is the fiber.
You think this is totally obvious?
No, that, I'm trying. I'm slow. Yeah, that looks okay. Yeah.
Good. Sorry, yeah. Okay, so, but anyway, so if this map is n plus m connected, that means n plus m of the homotopy groups of T vanish. But since it's also the fiber of this map, that means this is an isomorphism in homotopy groups up through dimension n plus m. Agreed? So this map is an n plus m equivalence. Okay? This is just a sort of restatement. Yeah.
This helped me. The identifying T as those two things is the 3 by 3 lemma.
Well, I think the 3 by 3 lemma identifies it as this way, but not necessarily the fiber of this map, right?
Well, it could also. What
There's
I'm saying is you draw the 3 by 3 diagram with Fi up on the top right and X on the top middle. Yeah, and then not X, not yet.
Yeah, okay. Yeah, so there's many ways to see this, right? Exactly.
You can also get the two pullbacks diagram with if the maps F and then I both go vertically down the right-hand side.
There's many who would do it. I had a different proof in mind, but this is essentially, they're all essentially equivalent, right? So
What you call the 3 by 3 diagram is the one that we saw at Guillaume's talk the other day.
So the 3 by 3 lemma that Mike has in mind is the following. You take any square. Okay? And now what I want to do, there's two things I can do. I can take the fiber here, so F, G, H, K. I can take the fiber of this map, which would be fiber of H. I can take the fiber of this map, G, which would be like this, and there's always an induced map here. And then I could take the fiber again and call that T. On the other hand, I could go as follows. I could take the fiber of this map, F sub F, and I could take the fiber of K, right? And then I have this map here, and I could take the fiber of this. And the point is those two are equivalent. So if you start with a square and start generating fibers like this, you don't have to, there's no ambiguity. This thing right here is the fiber of both that map and that map. And as I'm trying to say right now, it's also, sorry? It's also the fiber of this map. So now the diagonal is also a fibration sequence. Okay, it's all of those things at once.
Wait, somehow you haven't used the fact that W is the cone of F, which is highly suspicious.
What? I'm about to. What do you mean? This is totally general.
For any W?
For any square, yes. And yeah, for any square of maps, of base maps, this is true. Yes, yeah. Irregardless of whether it's a push out or anything like this, this is just, you can just get this by calculating with fibers. So, but what I'm saying is, in particular, when this is the cofiber, and we have connectivities of these maps, we get a connectivity estimate for this this thing right here. And in particular, it tells us that the fiber of F and loops on the cofiber of F are isomorphic up to dimension n plus m.
So in this case, Blaker's method is saying that the map from X to Fi is n plus m connected.
Right, right. In other words, I mean, I really think of Blaker's Massey as a theorem about the vanishing of how many of the homotopy groups in this total fiber.
So this is
These are equivalent things.
yes.
That's why I stated it this way, so that all these things are equivalent.
So T is n plus m connected.
Yes, as a space,
Okay.
which means this map is n plus m connected as a map, meaning it's an isomorphism for the first n plus m homotopy groups.
I see. That's another way of stating Blaker's method,
Yes,
so to speak.
yes.
So is n plus m equivalent?
It's actually n plus m connected, right?
Yeah, oh, say connected, right,
Okay.
as a map. Let's go over here. But what does that say? I mean, so the point is though that if I now look at the homotopy exact sequence, so y. So let me just start generating it this way. X. This is the fiber of F. This is pi q plus 1 of y. So we're looking, this will be pi q minus 1 of the fiber of F. The point is that in the range up to n plus m, we've just found out that this is equivalent to the loops on this, which means that, that I can replace this with pi q of loops on the cofiber. And I can replace this with pi q minus 1 of loops on the cofiber, because we just decided those were isomorphic in this range. So q less than or equal to n plus m. But if I just put a loops here, that just does this. When I loop the cofiber, I just bring its homotopy groups down by 1. So and you can see what.
Are you doing here without erasing?
Sorry, I'm really bad at that. So this gives me pi q of loops on the cofiber, which is pi q plus 1 of the cofiber. And then here, I get pi q minus 1 loops cofiber. And then that's pi q cofiber. Okay? So with these replacements, you can see that what I have is just a range of dimensions where this cofiber sequence, in fact, is exact in homotopy by just reindexing things. If you stare at, if I just applied pi to the sequence right here, pi n, I will see this picture. Okay? So Blaker's Massey, in some sense, tells you just this formulation, the way I've said it, is that this sequence is always exact. Based on the connectivity of F and the connectivity of the initial space, this sequence is sometimes exact. It's exact up through dimension n plus m. Okay, does that make sense? Peter's not happy.
Slightly reasonable. The sequence that you got to be exact was the homotopy fiber sequence, but you're able to replace the homotopy groups of the fiber with homotopy groups of the cofiber.
Right.
But isn't that still then going in the opposite direction from the actual original cofiber sequence? Oh, no, sorry. No, yeah, on that. Great.
So, but I'm not sure. I mean, the sigmas on under the homotopy groups don't show up. Right?
That's true. Yeah.
So it's not like applying phi 0 to this. I mean, which wouldn't make any sense anyway.
Yeah. Okay. Okay. Well.
It is an exact sequence.
Right.
It's not
Right.
something like that.
Okay, so it's not exactly this exact sequence, you're right. But in any case, the point is that it does let us compute the homotopy groups of the cofiber, at least in a certain range. Yeah. You're right. You're right. Okay. Does that make sense? So okay. So this is sort of what I wanted to say, and this is the beginning of the connection between. So in a sense, yeah, you're right. I kind of lied about that. It's not exactly the sequence. But what I want to say is that homology and cohomology are theories or invariants, unlike homotopy groups, which focus on this side, for which this sequence is exact, instead of that sequence over there. Does that make sense? In other words, they're theories which behave well when we glue on cells, when we build spaces inductively. Okay, and so you have the feeling that that, for example, when we present spaces in homotopy type theory as cell complexes based on higher inductive types, that their cohomology and homology groups should be easier to calculate than their homotopy groups because we have all the tools generated from these sequences. Okay. So, okay, great. Okay, so this is nice, but maybe it would be helpful to for me to now say, recall something about the ordinary definition, how people usually see cohomology presented. Okay, I mean this is a nice. I mean the reason I write things this way is because you can see everything I've done here is kind of in a sense internal to an infinity topos. I'm just talking about limits and colimits and exact sequences and truncations. So most of the statements I've made here, I think are essentially accessible to what we can do right now with a little bit of work. Writing out this cofiber sequence is going to be hard because of higher inductive types, but possibly manageable. Okay, but of course, no topologist. This is kind of a sophisticated look at what cohomology theories or homology theories might look like, invariants that respect cofibration sequences. But that's not actually the way most people originally have them presented. So let me do a small just example of how people usually see ordinary homology, and then I think you'll see that it is definitely more computable than homotopy groups, right? Have a lot of people seen ordinary homology? I don't know if this is like for people who, I don't know if this is a waste of time. If everyone here has seen like how. I
don't mind if you recall.
Okay.
Everybody who's seen it likes to see it again.
Okay, great. Okay, so let's recall the setup. Right. So let's work. I'm just going to do the most simple, naive version, and then I'm going to skip all the hard theorems in the middle, obviously, because I only have an hour and a half that say that this agrees with something else. So let's start with a semi-simplicial set. Okay, so x then is a functor from this category delta I and j is what people write up into set, and we think of the value of x at the n simplices as somehow the at n as somehow the set of n-dimensional simplices, and the face relations here encode some sort of geometric structure, right? Then we can do the following. Well, so let me just draw a couple dimensions here. So it looks like this. Each of these are sets. Well, what I can do is in each dimension, I can take the free abelian group on this set of thinking of each simplices as a set of generators. Okay. So what I'm going to do is, in other words, there's this functor here, the free abelian group, which sends a set into an abelian group, and essentially what I want to do in the next picture is just post-compose my semi-simplicial set with this picture right here. So what I get, and I'll write the result like this: it's z on the generators x2 with a set of generators x2, and then I still have these maps right here. And then here I have Z on a set of generators x1. And then I have these two maps right here. And then I have Z on a set of generators x0. Okay? And these are D0, D1, and D2. And this is D0 and D1. Now there's this very standard construction you can do when you have a gadget like this. So everything here is an abelian group. And all of these are homomorphisms of abelian groups. Well, the next thing you can do is you can turn all of the maps in each dimension into a single map, which I'll call boundary, like this. X1, Z, X0. I'll call this boundary 2 and boundary 1. And the formula people usually write is that the boundary is the sum I equals 0 to n minus 1 to the I d sub I. Okay? In other words, I have these three homomorphisms of abelian groups, and I turn them into one homomorphism, since these are now abelian groups, by just taking the alternating sum. So d0 minus d1 plus d2. And here I take d0 minus d1. Okay? And so when I do that, what I get is a map from this abelian group to this abelian group given by that alternating sum. And then the lemma says that with these definitions, that d squared equals 0. Okay? So in other words, if I take something here, anything here, and do a d and then a d again, I get 0. And this, the proof is essentially, I mean, it's totally, yeah. So it's the simplicial identities. So they just guarantee this. You look at the identities that you have after composing two of these maps, and then you sort of separate into two things. Anyway, it's fun, cute, so you should try it for yourself. But whenever you have a simplicial thing and you perform this construction, you get a case where. So in other words, people have a name for something like that. That's called a chain complex. Okay, and. A chain complex is a sequence of abelian groups and a map between each one such that their composite is 0, which is exactly what we have right here. Okay, we just started with a semi-simplicial set, and then we constructed this, and then we can now. It didn't have to be semi-simplicial; it could have just been simplicial, but you'll see why I chose semi-simplicial in just a second. Okay, and so what does d squared equals 0 mean? It means that the image of d I is contained in the kernel of di minus 1, right? So this is just a restatement of this fact right here. So definition, hn of x with coefficients in z is the kernel of dn modulo the image of dn plus 1. Okay? Does this make sense? So if I stare at anything right here, this composite is 0, which means that the image of d2 is in the kernel of this map. So so that means that since the image is inside and they're abelian groups, I can just form this quotient group right here. And that's by definition the nth homology of my space X. Okay? So is this okay?
There is another definition.
There are many definitions, yeah.
Well, yeah, that's fine. But there are many definitions. But one which is probably the shortest modulo, the things which people around here already know, would be to take this z functor, so to take the free abelian group generated by the semi-simplicial set, and then take the homotopy groups of this free simplicial group.
Yes.
And then don't forget that it's an abelian simplicial abelian group. Consider it as a semi-simplicial set, and take its homotopy group. So on the level of types, one should take a type, somehow make a free abelian group out of a type, and then take homotopy groups of that free abelian group generated by the type. But how to make free abelian group generated by a type, it must be one of the cases of higher inductive definition.
Right.
Because it's just a free element
Agreed. Right. Yeah. No, I was going to come back to that. In this case, I just wanted to do like one example to show you that that this isn't well. So what's not clear is that there are a couple facts about this. That this is homotopy invariant. That if X and Y are homotopy equivalent spaces, that's true. Moreover, so facts. And then I'm going to do one example so you can see that these groups, unlike homotopy groups, are in a sense combinatorial. You can just write them down from, or maybe that's not worthwhile. But so Hn is, well, I wrote it with z coefficients, so is homotopy invariant. Meaning that if you have, so Hn is a functor. This is essentially clear because it's functorial. This construction is functorial, and you just need to check that if you have a map, that it induces a map on cohomology. This is just easy to chase through. So this is functorial. It's homotopy invariant, meaning that oh, I haven't really said. I guess that doesn't really make sense to say with semi-special sets quite yet. But so this naive definition can be extended to all spaces in a very simple way, and in that case, it turns out to be a homotopy functor. And I claim that it takes cofiber sequences to exact sequences, but I'm going to have to spell out exactly what I mean by that a little more. So a consequence of the fact that this thing is just sort of combinatorially defined, and I wanted to just do one example to give you sort of the geometric intuition behind what's going on here. So let's look at an example of the torus. So here's a torus, I guess. So the idea is actually relatively simple. So if you have, let's suppose that I have a sequence of, say, like submanifolds like this inside the torus. I'm just going to take a sequence of little dots like this, and I'm imagining this one sort of living on the boundary right here. Well, so here's what I want to say is something like the sum of all these little one manifolds here, the boundary of it is 0, right? If I think of this little loop in here as a single manifold, it clearly has no boundary. If I think of it as like little pieces of one-dimensional simplices that have been attached to each other, then it also has, in a sense, no boundary, right? It's sort of the union of these pieces. And so, so that's encoded by this first step. To be able to sort of add little one-dimensional pieces or n-dimensional pieces of our semi-simplicial set together, it doesn't make sense to add them when they're just sets. But we can turn them into algebra by just taking the free abelian group and then think of their sum in this group as something like the union of those subcomponents. Okay. So this has this right here. It has no boundary, and that boundary operator there is meant to take that into account because you can see it counts vertices as positive and negative, and if I go around this loop right here, count each one positive and negative once, they're all going to vanish. On the other hand, this thing has no boundary for a very trivial reason, which is that it actually happens to be the boundary of a cell one dimension higher, right? So this d squared is 0 over there encodes exactly this topological fact for manifolds that if I have a manifold which is the boundary of another manifold, its boundary must be 0. Okay, but on the other hand, inside the torus here, there are other people call these things these formal sums of little pieces of your space, chains. One chains in this case, right? There are other chains in here. For example, oops, I guess that has to be dots. So I imagine this chain right here, which also has no boundary. But in a sense, this one is better than that one because this one has no boundary except for it's not the boundary of something higher. It's not the boundary of some higher dimensional piece, right? So so that's exactly what this definition is capturing. Things in the kernel you call cycles in your space, and things in the image of the dimension higher you call boundaries. And so by taking this quotient, we're exactly remembering those cycles in our spaces which were non-trivial in the sense that they weren't boundary of something one dimension higher. Does that make sense? So this ordinary idea of cohomology, I mean, I think this probably goes back to Poincaré, right? I mean, it's sort of very simple idea of sort of, in a sense, like counting holes, things that are cycles, things that have no boundary, but for non-trivial reasons. Okay, so just to be totally pedantic, so here, I'm going to just draw I've just drawn a little semi-simplicial set, and the letters are meant to indicate that some of these things have been identified. So my semi-simplicial set that I've drawn right here has exactly one 0 cell, all of these V's. It has three 1 cells, alpha, beta, and gamma, like this, and it has two 2 cells, U and ooh, that's supposed to be a capital V. Maybe I should call them something else, X and Y. So this is a semi-simplicial presentation of the torus after I make those identifications. So I maybe won't do the whole calculation, but you can see now what's going to happen. So in dimension, after I take the free abelian group on my set, let me draw my sets. They are V, alpha, beta, gamma. And then I have X and Y. And then I have Z on alpha, beta, gamma here. And I have Z on X and Y. Oops. Yeah, that's right. And then everything else is 0, right? Up through, there are no simplices of any higher dimension. Okay, and so I won't finish the calculation here, but you can tell if all of these are maps of abelian groups, you could just work this out. This just falls out. You can find all the homology groups in all dimensions, and it turns out that what I mean is you can just write down these maps, calculate their images, and calculate their kernels. Okay, and it turns out that the answer that you get after going through this little machinery, it's just a bunch of algebra, is that this thing is free on 2 generators here. I'll write them. Alpha and beta survive this process and live in dimension 2. And this thing is free on X minus Y. And it's X plus Y probably, you're right, okay. So in other words, we can just read off the homology groups of this space. They're Z in dimension 0, 2 copies of Z in dimension 1, and a Z in dimension 2, okay? So you can see, because of this combinatorial description, which I agree cannot be carried out at least as is in homotopy type theory, but because it exists in some sense, homology groups, unlike homotopy groups, we just calculated all of them for a particular space, right? I mean, it's a very, very trivial space, but and in fact, this method of calculation doesn't completely generalize, but I hope this gives you at least the impression that these groups sort of, in principle, are quite a bit more easily calculated than homotopy groups.
So, what are the homology groups of spheres?
Ah, okay. Well, that's easy to say. I was maybe going to drive that later. So, in particular, both. I mean, they're sort of.
You better write homology because you didn't define homology.
Okay. So it's Z. So I should say HKSN if k equals n, and it's 0 otherwise. You're right. Yeah. I'm looking for an eraser.